Okay, guys, assalamu alaikum. I hope that you hear me well. So today we are going to start the fourth chapter, talking about in the previous chapters, basically we have discussed minimizing the logic gates. And from that we came to know that about what is the K-map and how we used K-map either in 2 variables or 3 variables or for 4 variables. So if any one of you just here we give you like a review or the recap for what we have done before. Like what's the rule of 2 adjacents when we have 2 adjacent squares or 2 adjacent ones, how to group them and why we are grouping basically these bits together. So I mean the ones, and also in the same time then we studied that the don't care conditions when there is like no 0 or no ones, so that just we fill it with don't care conditions when we are not interested about the output. What is it? So the don't care condition, which we'll see it also later on, it depends upon the designing circuits which it's available with us and what was the output of that design, which it's not even in our interest. Then we came to discuss the implicants, the prime implicants, essential prime implicants, and the other, types of the rules that give us minimized expressions for the digital logic designs. After that, we came also for the discussion on how do the expression for the complement of a function from the K-map can be done. What the advantage of considering the don't care conditions also, we have also discussed this very well. We discussed also which gates are called universal gates, and for that we say that like 3 gates, which they are NOR gates, NAND gates, and the inverter one. Then we came why NAND gates and NOR gates are preferred, because from these gates we can build the full circuits and the full integrated circuits which we want, and if we have NAND gate we can convert it to ANDing gates or vice versa. So it is the universal gates, and they are implemented and easily to implement. Also they help in reducing the power and the cost and the propagation delays of the bits that transferred from the inputs to the outputs of the of each gate. Then we came also to know any circuit can be implemented using NAND gates only. Any circuit can be implemented using NAND gate only. Yes, there is many. This is a true like information. So we have seen that how we convert our gates if we have NOR AND gates or OR gates, how to convert it totally to be like an AND gates. And we have gone through this series and this lecture last time. Then why XOR gate is called odd function. Also we discussed this. We discussed also that the commutative properties and also the parity generators and checker of the errors or the bits at any bits when we transmitted from the transmitter to the receiver, so that if we send our information with 1 bit, so that it is like odd function or odd bits is there, and the output, when we have odd ones or when the inputs are like even ones, or when they are even ones, then we send like a 0 bit as a trigger for the even functions. Today, just come to our lecture. In our lecture, we will talk about the combinational gates, and what I mean by combinational gates, then we come to the combinational circuits. We will go through their analysis, through their design procedures, and through binary adders and subtractors. We will try to cover as maximum as from this chapter. I hope so that we can cover, like, if we cover half of the agenda here or outlines here, it will be more than enough for today. So let's come and define what is the combinational gates or logic circuits. Logic circuits, any logic circuits, when we can talk about it, we are talking basically about the logic gates and the outputs that depends only on the when output depends only on the present of the combination of the input. So if, for example, let's see here, look here, for example, this here is the output function, the combinational circuits. Now here I have my inputs. When these inputs, the n inputs, give me m outputs without any feedback or without any storage of data, this is called a combinational circuit. But if we give it like a feedback from the output, I mean some part of the output, we return it back to the input, this called a type of sequential circuits, means which we will study it later on. Or when we use registers, then this it will be called like registered or latched circuits, as we are going to study it also later on. But in this chapter, we are going only to focus upon the combinational circuits. So when input changes, output may change after a delay only, just because here, from here to here, the bit, the time propagation or the delay propagation for the bit to be transferred from the input to output, this is the only difference between input and output, so that the rest, as there is no any part of the output to come to the input. So when we talk about the combinational circuits, we are going to talk about one of two things. Either we are going to talk about the analysis. Analysis means that I have a circuit and I want to analyze this circuit. I want to analyze it means I'm going to make it as a Boolean function, and I'm going to make it is truth table. Okay, so I have basically, I have a circuit, as I can see from here, which I'm going to explain it to you and make it for you, inshallah, more easy and understandable when you come for analysis. You have to analyze it by taking it is Boolean functions. So Boolean function means that you are going to check each input and what is the result of each gate, then what is the overall results of this circuit, and then we take the truth table for that. So when we talk about the design, means that we have a truth table and or we have expression, and we want to design our circuit from that. So given a desired function, it's with us, but we have to design the circuit. So just this is the difference between the analysis of combinational circuits and design of combinational circuits. Again, I have to repeat this talk to you. Analysis means that I have a circuit which I want to analyze it. Design means that when I have a function and I want to build the circuit from it, and in the same time, I want to make the truth table. So I have, like the design one, I have inputs, and I know what is the inputs, what's the outputs, but how to design my circuit. This is the definition of meaning of the design. So few steps are there if I'm going for the circuit, I mean for the analysis of the circuit. First of all, I have to determine every input and output is coming to the gate or going from that gate. So determine the number of inputs and outputs. For example, for n inputs, list all the binaries from 0 to 2 power n minus 1 in a table. Okay, then we have to determine all the output gates, which we'll see it again. We have to determine the Boolean function of each gates. We have to determine or obtain the truth table of those gates, and then we keep just repetition of number 3, step number 3, which it is determine the Boolean function of each output. So let's say that this equation, this circuit here has been given as example number 1 in the book, and we are trying to analyze our circuit. Analyzing our circuits, as I told you, that first of all, we have to define each input. So in the gate number 1, which is AND gate, each input has A, B, C. The other one, it has A, B, C, but it is OR gate. The third one here, we can see it, it's AND gate with 2 inputs, A and B. The fourth one, it is AND gate with A and C. The fourth one or the fifth one, it is AND gate with B and C. If you can see the last 3 AND gates, they are basically ORed. ORed means they are, you remember that we were talking about the sum of the product. Sum of the product means that I have a product. Product, what does it mean? Products or multiplication in Boolean function or Boolean algebra or digital logic design means ANDing. Okay, so ANDing the gates here, it will give me, I mean, when I OR these 3 functions, I will get a result. This was the first step. I have to label each inputs, and in the same time, I have to label each output at the gate. So let's say that the output of the first gate, for example, which it is ORing gate, we call it like terminal 1 or T1. Again, if we come here for the other one, and we give the terminal here or the T2 as the output of the AND gate, this one here as mentioned. The third one here, this one, what is their outputs here? It is here, F2. And if I take the value here, which it is F2, and I give it inversion here, what I will get? I will get F2 prime, or the complement of F2. Now, in this gate here, basically I have T1 is coming and F prime 2, but both of them, they are ANDing, means that I'm going to multiply both of them. And let me call their output as T3. So this T3, it can be ORed with T2 to form F1. Let me make it in more detail for you here. Okay, in more detail, the same one, but it's in more and explicit form and easy way to understand. I have this circuit. Let's say that the output of the first one, which it was, for example, T2, which we call it, what is the output of this AND gate? It is ABC. Simple is that. And this is, we have done it in chapter 2 and chapter 3 as well. So let's see again for the other one, for the A, B, C of when we OR them together, means that I'm going to sum them. Just I will add plus between them. So again, it's very simple when you define your work and segment it. So at the end of the day, you will come to a good result and a clear result without any mistakes. This subject, as I told you, it's a subject of full understanding or no of understanding. I mean, maybe you make a small mistakes which will make all your result wrong. So you have to be very careful in simplification and don't jump on the steps until you have the full of experience and you have the visual power that it allows you to read the things in a whole picture and get the result. But as a student, I prefer that You go through them step by step. Come to the third one here. ORing these functions together, which it's A, B, 3 ANDing gates, what will be? Sum of these multiplicants or multiplication or multiplied gates. So it is ORing of the ANDing ones. AB, the first one, this one AB, the result it's AB here as ANDing gates plus, because it's ORed function, plus AC, the second one, the third one, plus BC, it's this one. Now, the three terminals here, or the three outputs of the first level, I can call it. You remember that I told you that how much, if we come to see how many levels here I have, or how many levels of propagation delay for the bit to be transferred from A to from the input to the output. This is level number 1. Then from here to here, level number 2, level number 3, level number 4, and level number 5, right? So each gate of this bit transferred from here to here needs a time. Transfer from input to output needs a time. Again, when we invert it, it will need some time. Again, when we invert it, you remember what we have done in the last lecture when we were discussing the Verilog, how to, when we write our module programming for that, just what we said, we give every input, we give it a small time. That was a nanoseconds, for example. It was in the first example, which we have done it, that we give the ANDing gate 30 nanoseconds. Then we give ORing gates 20 nanoseconds. Then we give inversion, it's like 10 nanoseconds. This is just example. I mean, the designers, they give the time which they want. But at the end of the day, this is not my issue now to explain it here. I mean, to come back to the previous lecture, which we were explaining. No, here just I'm telling you that when we defined our work, it became more easy. And here, what we got from this results, just we finished the first and 2 levels of the transfer of the bits from their gates, from their inputs to the outputs. So come now, if I take this, now F2, now it's very clear that F2, it is AB plus AC plus BC, because just it will come on this line to here. But if I take this AB here and I pass it through the inverter, through not gate, not function, okay, what will be? It will be primed, right? So when it will be primed, what will happen? Now here we have to apply again. You remember that the De Morgan theorem from chapter 2. What was that? That was the multiplications of 2 bits can be ORing, ANDing. It has been converted to ORing. And the ORing, this one, it has been converted to ANDing between them. Again, for the other one, ANDing, it will be converted, instead of dot here between them, it will come here like ORing or plus. Again, if we come to the ORing one here, what will be? It will be the ANDing. So, and so on for BC as well. This was first step, transfer your gates, or shuffle your gates, or transform your gates from ANDing gates to ORing gates and vice versa. One. Second is taking the complements of these elements. So instead of A, B, they became A prime and B prime. The other one, instead of AC, it became A prime, C prime. Then all of them, they became prime. B and C, it became B prime, C prime. This is simple way, right? Okay, now come, if I take this data, the result of the inverter, and I pass it through ANDing gates. So ANDing gates means that I'm going to multiply it with the result of the OR function here, which I have it ABC. So I have to multiply this value by this value. What I will get? After simplification, which as we have done in chapter 2, just go through them, multiply both of them. I mean, this function, you multiply it with these functions, you will get the result, this result. Next time, when I meet you in the class, I will request one of the students just to go through this simplification. It's very simple, and also you can check it from the book. It's very simple, but what I want you to do, I want you again to revise your memory, reactivate your memory, and just go through their simplification. It's very easy one, and it's not difficult. Now, this result from here, okay, let me give you the hints. These here, for example, if you multiply this value by this value, what you will get? A into A prime, so it will be 0. A into B prime, it will be there. And A into B prime to C prime, this is the first part, this one. And come here, B to A prime to C prime, it will be again here. Then C to A prime and B prime will be here. The main thing is that just you are going to cancel A to A prime, or B to B prime, or C to B to C prime, according to the postulates and the theorems, which we have done it in chapter 2. Okay, so this is the simple way, I mean, of their simplifications. Now, if you have this result and just pass it through OR gate, OR gate means I'm going to multiply it. I have to add it with ABC. Then I will get this result. I will get this result. A, B prime, C prime, plus A prime, B, C prime, plus A prime, B prime, C, plus A, B, C. While as I told you about the second one, which F2 already we have done it, and we have get it here, AB plus AC plus BC. Now, what we have seen from this one, the analysis is completed as Boolean functions has been implemented and expressed, written in a very well way and in a very clear and easy manner. If I tell any one of you, if you did not go through these types, through these steps and implementations, I mean, if you did not define it like that and just you jump to F1 and F2 and you want to calculate their outputs, you might get a mistake because you will get a lengthy expression to be used. So the best way, again, you have to first of all calculate each output node. Then at the end of the day, you will get your results. Now, after this, what I'm going to make? I'm going to make the truth table. Let's say that here, A it's equal 0. When just I give everyone 0, 0, 0. Like for example, at the beginning 0, 0, 0, right? For 3 bits, if I can see here, I have 3 bits only. A, B, C. For the first one, A, B, C, then A, B, A, C, B, C. So 3 bits are there. So let's say at the beginning level, or when all of them they are zeros, what will be the result? The result of the first one is 0. The result of second one is 0. Their result will be 0, right? And these 0, it will come. So now look here. The only difference is here. Why? Because when we OR all these 0, it will give you 0. But according to our our circuit design, that we are using the inversion here or NOT gate. So NOT gate here, what it looks like, it will invert the 0 to be 1. Now, this 1, when I pass it through ANDing gate and multiply it by 0, it will give me again a same result, 0. This 0 again, when I XOR it with other 0, when I OR it with another 0, it will give me the result of 0. So what will be the output then? The output of F1 will be 0. The output of F2 from here, it will be again 0. Come, if I change only 1 bit, for example, I have 0, 0, 1, means that C has been changed, right? C here in the gates. So this function will be A, B, C, which has been changed. At the end of the day, when I multiply this, it will give me 0. But the thing is different. When I OR it with A, B, C, it will give me the result of 1. And here it will give me 0 as there is no C. Here, as it is AND gate, give me 0. As AND gate also, it will give me 0. So where I will get 1, I will get 1 only here. Right? Now look how the things are different. Now, ANDing this one with the inversion 1, which I got it from F2. What I got 0. I got 1. So this one, now when I OR it with another 0 from any gate, because 1 plus anything, it will give me 1 in a Boolean function. So the result will be 1. Now, means that F1, it's equal 1, while F2, it's equal 0. Okay? So I think now it's clear things, right? Come again now, if I change the bit B, this one, if I change it to 0, while A and B and C are 0, so from the truth table, which we have it, 0, 0, 1, then 0, 1, 0. Just let me change this, what I will get, what type of results I will get. This one definitely 0, but this is again 1, this is 0, this is 0, this is 0. What I will get? Let's see. The same result as in the previous one, I will get 1 and 0. Now, let me, if I change 2 bits, now, if I change B and C means that without changing of A, again, this will give me 0, this will give me 1, this will give me here 0, 0, but the other one, the last one, BC, will give me 1. So the ORing function here will give me 1, whatever this it is, but this one's ANDing gate here, the result of 1 here plus anything, it will give me 1. So I have here 1, which again, it will be here 0, as I can see that, while this one is here. So when 1 is here with 0 from here, again, I will get 0. So the function 1 will be 0. While the function 2 is 1. Okay. Now, what I'm doing, I'm just trying to help you to understand what we have done it in chapter 2 and chapter 3. That I'm going through the simplification of the truth table and how to implement it when I have a circuit, how to apply my 0 and 1s. So these things also, it will help you in the lab. When you go to the lab, just you will change switch on and off. The same circuit you can build in the lab and just manipulate with their inputs, and you already know what is the output will be, the expected results of the output from your diagram. And you compare then your results with your experiments which you are doing. Again, go for the third one here. For example, if I change A, it's equal 1, I will get the same result as you can see. If I go now through all the truth table here and just I come to the end to see when I get 1, 1, 1. When can I get 1, 1, 1? I get 1, 1, 1 when all these outputs are 1. So when all of them, they are 1s, then here I will get due to this inversion 0, which this will give me 0. But at the end of the day, it's ORed with the first NAND and functions, which it will give me 1, while these 3 are 1s. So they're ORing, it will be 1, and the result will be 1. Only in this case. Now, we finished the truth table analysis, right? We finished also the circuit analysis by Boolean expressions, right? Now, one more step remain. That is the Karnoff map. How to make it on K-map. As I have 3 bits, A, B, and C, means that I will have 2 power 3, which is equal 8, right? So I have 8 squares. 8 squares means I have 0, 1, 2, 3, 4, 5, 6, 7. Okay, this is Karnoff. Just now I will see. He wants me to implement F1 for Karnoff map. Yes, F1 where it is available. If I take the MINE term for that, Min term means that I'm just going to focus on the ones available in the f functions. So it is available at 1, it's available at 2, right? It's available at 1 and 2. This is 0, this is 1, then this is 2, while this is 0. Because this is f, this is 3. No, I am talking about 1 and 2. Then come again about here, then what we said here, 1, 2, 3, 4. This is 4. Then 5, 6. This is 6. This is no, this is 7, because here this is 6, this is 7. So now when I have them, what I can see that I have here A and B 0, 0, while here BC 0, 0, 0, 1, 1, 1, 1, 0. So I have the value. Just when I have it like this, you know, it's another easy way to build your Boolean expression, which we have done it through the simplification of taking the values from each output. You can again get the same result here by using the Karnaugh map. Simple, 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 very, very easy things. I mean, what you have to do only to solve your functions in 1 or 2 ways. I mean, the first one, it was the Boolean expression that you go through the mathematical model as in chapter 2. The third one, which you solve it, you take the Karnaugh map as you have done in chapter 3. It's the thing is not difficult, but the thing is that only just you need to make a more practice and you have alternative solutions. Then you have to check your F1, which you got it here, with the F1, which you got it from the beginning one, from the first expression, which it is this one. Okay, so just compare them and then you will see how the result it is. Now, come for F2. For F2, what we have? We have a values at 0, 1, 2, 3, right? This is 3. Then 4, then 5, 6, 7. 5 and 6, 7. Again, minimize your circuit. How you will minimize it? You will take the adjacent squares together. So these ones together, you can take them. And when you are going to take this, this is the area of B. Area of B, what I mean by area of B and area of A and area of C. Here I have as previous one, like you remember that in the previous time, what we were saying, like we were saying like this one, this is A here, right? And what is here? B and C. Okay, so this is 0, 0. This is 0, 1. Just let me write it like this: 0, 0, then 0, 1, then here 1, 1, and here 1, 0. Okay, now you can see that B here is fixed, right? B here it's 1 and here is 1. So it is the area of B where B is fixed. Come here to this one. A has been changed from 0 to 1 and come to then the other one here. I mean, so when we take this group, just we can say that A here is fixed and B is again fixed, right? So it is AB, the first one. First part, it has been constructed. Come this one, then come to the second group. Then take these 2 adjacent squares or 2 adjacent ones. Which one is fixed? Here, C is fixed. C, because here C is 1 and here is 1, while B is different, so it will cancel each other. What also is fixed here? A is fixed, so it is A, C, this one. Come to the third one now, the most isolated bit, this one. Now, when I take them together, means that A is changed from 0 to 1, while B, C are fixed. So this is the BC. Very simple. So we have constructed our table even for F2 functions. So again here, I have to give you the conclusion for that. for designing the procedures of any circuit, we have to determine the number of inputs and outputs from the circuit's functionality. Then we draw the block diagram without the internal details. I'm not interested about the internal details. Just I will have, when I have a circuit or something like this, I have to determine how many inputs I have, how many outputs I have, and then I go through building this, or analyzing to build the function without going in more details about the internal function is going. So this is exactly similar to the function prototype in the programming. So the third one also, the second one, derive the truth table for each function which we have done. Third one, simplify the expression by taking the adjacent values together, the adjacent ones, or taking the common factors between them, or minimize your circuit as maximum as you can. Fourth point is implement the circuit, which you can. So let's take one example that called code conversion example, or design a circuit that converts from a BCD code to XS code. Okay, so some circuits uses XS codes, and we need to feed the circuits with the right input. Okay, so very easy to complement this. For example, if you say 9 minus 1, it's very easy to complement it and to obtain it by inverting the digits. We will come to it, and let's see in more details. When I talk about the BCD is from 0 to 9, right? This is the BCD, not more than that. I mean, when we are talking about the BCD, I'm talking about the 0001, or about 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So the digital conversion, the digital representation of the decimal bits up to 9. After 9, it's not my issue. I mean, it's not, under the BCD. Okay, so if it is greater than 9, we will see it later on that how to bring it to the place of 9. Okay, of BCD numbers. So if I have any bit, any bit of these, if I have any bits of the BCDs, for example, I have 0, 0, 0, 0. What is the, for example, the first XS3 input? It is 0, 0, 1, 1. What is this? This is basically, I have the bits plus, I have the binary plus 3. Plus 3 means that this is 0, this is 1, this is 2, and this is 3. This one. They are totally similar to each other, right? Now, if I take the, for example, if I take this one, 0, 1, 1, 1. What's it? 0, 1, 2, 3, 4. 4 means that 7. I'm talking about 7, 1. Let's come here. See, this is this one, right? So 0, 1, 2, 3, 4, 5, 7. So they are similar. Only just what I have done here, I give it plus 3. Come to the last one. For example, come to 0, 0, 1, 1, 0, 0, or come to, yes, if I come, for example, to a bit here like 1, 0, 0, 1, 1, 0, 0, 1, this bit. Okay, so what I can see from this, from all these things, is that XS3, only I have the binary numbers, which are not exceeding 9, and I give it plus 3. So 0, 0, 0, 0 is not available in XS3 codes. The first input in XS3 codes is 0, 0, 1, 1. Okay. Look, for example, if you have 0, 0, 0, 0, then you add this with 0, 0, 1, 1. Just add them together. What you will get? You get the value of 0, 0, 1, 1. And now if you have this one, 1, 1, 0, 0, and add this with the first with 3 bits. I mean, when you give it 3 bits, what you will get again? You will get another value. Let's come and talk about it. So what I can see here from ABCD or BCD, if I have 4 inputs and their values from 0 to 9, as I said, and the output definitely will be 4 outputs, 4 bits from 4 bits value plus 3. Let's talk as conversion here. What we can see, I have input BCD for 4 inputs, and I have also the other one here. It's the code output access 3 codes. So what I can see from this table, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So this is are the 9. Come here, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. If I can see that the first 4 inputs, they have 0 W. From where this I can get this value? From here. Let me just mention this a very small point. That's it. For each input, for all these inputs here, I will have 4 different outputs. So the first output is W. This one. Let's make it is Karnaugh map, which it is this one. If I have it 0, 0, 0, 0, 0, 1, 1, 1. What I can see from that, this is representing the first m square, second m square, third m square, fourth m square, fifth m square, sixth m square, which it is this one, which will be this one. Then seventh m square, this one, which will be this one. Then 8, 1, then it will be this one, and so on. Okay? So what I can see up to 9, this is 9, right? So this is 9. Okay, what about the others? The others don't care function. This one, and all these they are don't care. And as there are 4 inputs, so I have the Karnaugh map with 4 variables, A, B, and CD, right? So I will fill the other gaps here with don't care functions. So don't care means that I am not interested about their inputs. Now, when I have it, recording.